Okay. Last video, we designed the slab, and that's exactly what you need to do in your project for your floors and your roof. Okay. Now we're going to design the beams. And again, this will be what you need to do in your project. Here in the example, we're going to do interior and exterior. However, you only have to design the interior beam. Okay. So how are we going to find the loads? This number right here, 252, okay? That is your pressure in PSF, okay? So that's the loaded area that we found. When designing this slab, right? We found that pressure. So when we do the load combinations, this is what we found, right? That is the load pressure that is on, let's say, on top, right? Of the slab, right? You multiply by 1 to design your slabs, and you multiply by the tributary width of the beams to find the value for the beams. Okay? So that's what the example shows here now, that you're going to multiply then for the interior beam, you're going to multiply by the tributary width to come up with the effect of this pressure into the beam, right? So we have that pressure multiplied by 16, which is the tributary width of the beam, right? And you still need to add the weight of the beam web, right? Because we didn't have that. So we need to add that portion of the web here. And we know how to do that. So to this weight that is already factored, right? We're going to add the weight of the beam that is below the slab. Right? And we multiply that by 1.2 because it's a dead load. Okay? So that gives us a value of 4.33 kips per foot. No? So 17 inches again, only the web portion, because the slab weight is already included here. Okay, so now that you have that and you have your load, you're going to put your load in the beam. Now, in this example, the beam is simply supported. In your project, which is what you already submitted, right, you have a continuous beam. And this is what you found already. You should have had this load, put it there in the continuous beam, and then using the coefficients, right, you found your moments. Okay? But this one is simply supported, so that's what we have. Okay, so 26 feet center to center, clear distance 25. And we find our moment, right? WL squared over 8. So for those that like to copy, step by step without thinking what you're doing, this equation right here is only valid for this case. It is not valid for your project. Your project, you have to use the ACI coefficients. Okay. All right, so I got my moment positive, 365.9. So I'm going to design my beam, but now I need to find my flange, right? So I had 3 things I had to calculate. BW plus ln of the beam, right, divided by 4. So 14 inches is the width. The clear value for the beam, 25. Right? You can usually assume 1 foot less. So typically about 6 inches on each side. It can be more, but that's a good estimate. Okay. So you get 25 times 12 divided by 4. That gives me 89 inches. The next one is BW plus 16 times the thickness of the slab. The slab is 7 inches. So multiply by that gives me 126. And the center to center spacing is the tributary width. So that's 16 feet. That's 192. And therefore, the smallest value is 89. So I will use 89 as my flange. So my dimensions of my beam are like that, okay? So 89 is slab 7 inches, web 17. Yeah, this is not right. That's 24. So I don't know if I can edit this one. So that has to go to match this one. Okay, so that's much better. So we got that. All right. So MU, your moment, which is this one, I round it to 366, has to be less or equal than your phi m sub n. That one, we have the formula for that one, remember? So again, we need to find a d minus a over 2, right? Which we're going to replace by 0.9d. You can always do a quick thing like 24 minus 2.5. That's perfectly okay because you're going to check it later, right? So you can do that. Or you assume a bar and stirrups, then you would do the calculation using that, and you get 2163. Mm-hmm. All right. So you assume also a phi factor of 0.9. Multiply your moment times 12 to change this to inches. I mean, that's an error that happens quite a bit. Okay. You need to multiply by 12 because your area is going to be in inches. Okay, so you have to add the 12. All right, so that gives me AS for 18. I check for my minimum. This one controls. We knew that already because the value of this concrete is only 4,000, which is less than the 4444, right? And so that one controls. With that, I find my A value, right? That can be found by the formula or by equilibrium, right? You can use equilibrium and find your A value. Notice that the B that you use here, right, is the 89. Why? Because your compression is on the top, right? So we're going to assume that the compression is going to stay here on the top and it has a width of 89. So that's why you have to use an 89. So you use the 89. I give you 0.83. 0.83 is definitely within the 7 inches of the slab. So this is a regular rectangular section with a B of 89. Okay. So we again do the calculation for the area using the A value. Now it's 383. It's still greater than the minimum. So we go and look for values. And we have, 4 number 9s, 5 number 8s, 3 number 10s, 6 number 7s. 4 number 9s is fine. Okay. I just pick 5 number 8s in this case simply because the diameter, right? 1 inch, so easy to work with. But then this one is easy to work with the areas because the area is 1, right? And so we will have those in there. So different options, right? This one would be good for construction purposes because you have less bars, right? Actually, no, this one will be even better, right? 3 number 10s, perfect, right? Because for construction, you are lifting that now. Now, the 6 number 7, probably you want to control cracking, but then that one went past the 14. So that will put you at the 5/8 to control more your width of the cracks. Right? So next, we're going to check our ductility, right? And so since we selected A number 8s, and we assume here, for this number, we assume number 8s, then we have the same number. It doesn't change. So it's the same number, right? And we find our new A value, 0.78. And that looks, okay. So this one right here is not right. That's, we're using 89, right? So we're using 89 here as our value, right? Which is here, 89. Now, since A equals 0.78, again, is within the 7 inches, everything is okay. Your rectangular section, we check ductility. We got plenty of ductility, so we are good. Phi factor will be 0.9. We find our formula, our moment using the regular formula for rectangular sections. and our value is 377.5. That's definitely bigger than the 366, and we are good. Next, we're going to check cracking control, right? We are using 5 number 8s, so it should not be a problem, right? I mean, you can do a quick calculation and say, well, if I have 5 number 8s and this is 14, I do 2.5 on each side. That would be 5 approximately. That gives me 9, and so 9 divided by 4, right? And so that would be your value, so a little bit higher than 2. So you're pretty good, okay? You want sort of a more precise value, you can do this formula, which is in your design aids, and you get 2.38, right? And so that is there, right? We're going to use 2/3 of Fy. My C sub C is to the bottom of the bar, so it will be 1.5 plus the stirrup, right? So they give me 187.5, 10.3, 12 ton. So yeah, this will be okay, right? So we don't have to worry about it. The beam is not deep enough, so we don't have to put a skin reinforcement. Okay? So for beams, as I said, you can do a very quick check of these almost mentally, right? And you can say that. I mean, you can say that. Okay. So the number of bars are 5. The spacing is going to be close to 2 inches, so that will not be controlled. Yeah, that's it. Done. Right? You don't have to do that. Now, I don't know, we got this 231. I think it's 238. All right, so 238. And so we are good. Well, I better check. Maybe it was 231. So let's see, it's 14 minus 3 minus 6/8, and then minus 6/4 equals, and you divide by 4. Wow, none of the values are right. Okay. Let's see again. 14 minus 3 minus 0.75 and minus 1.5 equals, divided by 4 equals 219. Wow. So none of the values were right. So 219, 219. Okay. All right. All right. So that's the design for that one. It's done. You're finished. All right. Now the exterior girder is going to be the same. The only difference is that your tributary width is different, right? So tributary width now for that one, see, we go from here to the edge, right? We'll be doing that already. So that will be 7 and 7 inches, right? And again, it's still simply supported. So it will be the same. So here the only difference is the calculation of your B sub F, all right? So notice that you multiply by the tributary width, you add the weight of the web, and that gives you your load, right? Oh, man. Why are these things so much different? Oh, let me see what number I've been using here. 221. Okay, so that makes this one also 221. All right. So 221, and then that's your load. This is your span length, right? We find the moment. Again, this formula only because is simply supported. In your project, you have to use the ACI coefficients. All right, so my moment is 187. You're going to find your B sub F. You have, again, 3 equations. One is with ln over 12. The other one is with 6HF and 6 times the thickness of the slab, and then half of your tributary width. Right? And in this case, the tributary width was 14 feet, right? And so this is center to center, so that's why we're subtracting the 14 in there. I'm going to change this one, which is I don't like it, simply because that symbol was used mostly for exponents. We're doing Excel sheets, and so for other things. So I don't want. So that looks better. All right. So again, you look at the numbers, 39 controls. So that will be your value, right? In there, and that's what we have. Mm-hmm. All right. Once we have that, I mean, we had the same. We have the moment had to be equal or less than your design value. Again, you can either assume a D based on bars and stirrup, or you simply subtract 2.5. Okay, you're still the same. Here I got the same problem with the figure, right? So I need to put that one down. And there. Okay. So we solve for that, get a yes, right? Check for minimums. We are good. 199, we're getting close, right? Check for A again. A is within the flange. We're good. Our assumption is good. So perfect. So we recalculate now the area of steel. Not much difference. 197 is still greater than the minimum. And so we have a couple options: 2 number 9s, 3 number 8s, right? And then we're going to check for our assume phi factor and all that. So we're going to take the 2 number 9s here, and so I do 2 number 9s using the, wait a minute, that doesn't look like it. Yeah, 2 number 9s, 112, 8. So that gives me a different D because I'm using now number 9s. My T is this. By equilibrium, you find your A, and you use here B equals 39 because your compression, right? Your compression is here where the 39 is. So you have to use the 39, not the 14. Okay, not the 14. So 39, that gives you 0.9, is within the flange of the slab, so it's rectangular, so it's good. Find epsilon T using the formula. This formula is in your design aids, right? And ductility is good, so phi factor is 0.9. A is maximum is satisfied. I should put that one here. I didn't put it on the other one. A is max, right? So A is max is satisfied. A is max is satisfied, so you have it in both cases. So fees men, you satisfy 190, 187, you're good. Check again, cracking control. You can do, a quick check. Here we're going to be a little bit closer to the limits because we only put 2 bars, right? So we got 2 bars. And again, this is 14 inches. So 2 bars, 14 inches, you subtract 2.5, 2.5, that's 5. You get 14 minus 5. That's 9 divided by n minus 1, which would be 1. So 9 divided by 1. So spacing should be close to 9 inches. Okay, so, and the exact value, you use the formula, is 875. Okay, and so 9 inches, so 9 inches or 875. So that's a quick check. Notice that you are below the numbers, so you are good. Okay, so as I said, the spacing on the beams can be done as a quick check without having to run so many formulas. Okay. All right, so this is what you have then, 2 number 9s for the exterior, and there. Now, here what I did is, since we have plenty of ductility, right? We have plenty of ductility, as you can see here, right? Plenty of ductility. So if I change this to 237, that is an increasing area, but not a lot to change this, okay? And so I changed it to 3 number 8s for another reason, because now I have everything 8s, right, at the bottom. So we can do that. In buildings, I mean, we seldom extend the slabs. Yeah, we don't increase, we don't widen the slabs. And so this is okay. You should do that because there's less moment here, if there is less moment. In bridges, you have a slab like this. You want to keep the same value that you got here. You want to put it here because in the bridges, you may extend that as traffic increases, right? And so it becomes an interior. And so you want to have that, okay? Just for the future. But that's one way of doing it. In there, of course, other options that we would have is, let me see here what we got. So this is this one. Looking at the steel. Yeah, we could have used 4 number 9s, right? 4 number 9s and then keep the 2 number 9s. Okay? So I could have put 2 number 9s, right? So I would have 2 number 9s, 4 number 9s, 4 number 9s. So you can see there are different options that you can do in order to work. It's better to have uniformity, okay, because it's a lot easier to deal in the field. Okay, here is another example. This is a plan view of a balcony. So these beams are coming out like this, right? And so your balcony is here. This is your balcony. These are your columns, 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 and this is a main girder here. Carry all these beams, right? The direction of the bars goes in that direction. So you're going to put your bars like this, okay, for the slab. Okay. And this balcony has 12 feet out. The whole thing is 48. And so we're going to design this. The load of the slab is a 7-inch slab. 7 inches, okay, so given that. Otherwise, you had to find it, right? How? Using the table, right? For span to depth ratios, and you do that. Here are your loads too, right? So tributary width for an interior beam, 6 feet, all right? Think of that. Now, because really you have a support, and a support, right? Some of the load is really going here, okay? Some. But that's a more advanced technique, and hopefully you learn that in the advanced reinforced concrete class. Okay? But for our purposes, I mean, we have 12 and we have 6, so the ratio is 2. And so we can say one way, right? So we're not doing a two-way distribution. So that would be that. So this is a conservative approach. Right? So everything goes to these beams. Some will go, really. Not everything, but we do that conservative design. So weight of the beam, stem, we don't know because we don't have a size of the beam, right? So remember, you assume a value, right? I'm going to assume a value. And then I'm going to find my load here, my 30 here, 87.5 for the weight of the slab, multiplied by the tributary width, and then the weight of the beam that I assume, that gives me that in pounds per foot. And then my live load, which is 100, and multiplied by the tributary width, that's 600. I do my load combinations, of course this one controls, right? And so that's my load, rounded to 0.93. And then I found my moment, because it can deliver, is WUL squared over 2. So here is my moment, right? 139. And now we're going to design, right? So when we design, we have the option of either you assume the dimensions and you find steel, or you assume the steel indirectly through the epsilon t, and then you find your dimensions. So we're going to do that, okay? Because that works for any kind of load. So we're going to do that one. We're going to assume then 001 here. That gives me my raw value. So we're going back to the design of beams that we did in the previous chapter, right? So we set up the equation, replace this one by 0.9D, replace the area of steel by rho BD, and you get a little table, right? So we're back to the table. So by now you should be able to do this, okay? So back to the table, so these are your options. You can have a B of 17 with 17.6, a B of 12 with 16, or a B of 14 with 14.9. Just to have enough space, I'm going to pick 14 and then 14.9. So I add my 2.5, 17.4, and make it 18. Okay. So notice that I don't have exactly 1.5 ratio, anything like that. So this is just reference values. Okay? Reference values. Unless I ask you, I mean specifically, I want this kind of ratio, then yeah, you have to do it. But normally I would say close to, so that way you have some leeway. Yeah? Okay, so we got that. We're going to check the minimum, H minimum, right? So it's 12 divided by 12 inches, change it to inches, divided by 8, and that gives me 18 inches. So then that's okay. 18 inches looks good, all right? So to satisfy the minimum, we're going to do that. We're going to check the beam weight. We need the weight of the beam below the slab, right? And so that's 160. It's greater than 100 by 60%, right? By 60%. So let's see what happened to your moment. Okay, so you, again, to give you an idea of how much a 60% error in your weight beam, how much error will cause in your moment. Okay? So you got here the D again, new dead load, go to your load combinations, you get that one, 144, right, versus the moment that you had here at 139, okay, 3.6%. Okay? Most likely this one probably would have been designed as 140 anyway, right? So you can see that a 60% error in assuming a beam weight, right, only has caused here an error of 4% in your moment. So when you're in the exam, don't sweat it. I mean, don't say, oh, I need this table, I need to do that. No, you assume a value. You work it out, you check it, okay? That's all you need to do. Please. So don't get stuck in the exam simply because you cannot find a way to the beam. Okay? This is just a very small thing affecting your moment. Okay, so we're going to keep the same dimensions as we found before, since this is a very little increase. My D value assumed would be 15.5. The area of steel that goes with this table, right, will be this raw value, which is that's the value I use for the table. So I had to use the same value. So now, unless the minimum controls or something else controls, yeah. But then you will use this one. We multiply by B and D. So we take that number, multiply by B and D, and this is my area of steel. So I need to check the minimum, right? But the problem with the minimum here is that, where is the tension? The tension is on the top. It's a cantilever, right? For cantilever beams, right, or beams that have flanges in tension that are determinate, right, the formula is a little different for A is minimum. And so we cannot find it unless we know the effective width. So we're going to find the effective width for that beam. Again, we use the three formulas. The BW plus the ln over 4, that's your clear distance, right? It's 12 feet. So multiply by 12 to change to inches, divide by 4, add it to 14, you get 50 inches. Okay? Then the other one that has 16 times the thickness of the slab. And then finally the center to center spacing, which is 6 feet. So out of the 3, 50 governs, and that's your width. Okay? Now I can check my minimum, because my minimum is the same equation, but your B value is replaced by the value that is the smallest of these two, right? So one is B sub F, which in this case is 50, or 2 times the web width, which is 2 times 14, 28. So 28 replaces now the B value. Okay, so here I will use 28 and not 14. Okay, so do not use 14 because tension is on the top. You will have to use this, and in this case 28 is the value to use. Okay, so with 28, these are my minimums, so it's 145, and so my value then compares well to that one, right? We're 241, 145. Now, the reason this is done and you get a higher value for these cantilevers and all that is because there were failures before due to minimum amount of steel using just the 14, right? Because you use 14 here, you get very low values, right? Half of this. And so that happened not to work. And so we bump it up this way. Okay? So that prevents any potential failure that may have there. Okay, from equilibrium now using my 241, right? I will find my A value. But notice now I use 14. 14. Why? Because my compression is at the bottom. My width for the compression is 14 now. Okay? 14. So I had to use that one, and with that one I find my A. With my A I find a new area of steel, and with that I go to the tables and I get 254. That fits well on the 14 inches. So we are good. Now that I know the size of the bar, I'm going to find my actual D and D sub T. And now what is this thing about this 225? This is something that I have not explained before, right? But you're going to put your bars here, right? So these are your beam bars. And this is your slab. But your slab already has bars, right? Your slab has bars that are going in this direction, right? That's your longitudinal steel, right? Going that way, right? So we go back here, right? You have bars going this way on this slab, right? You also have bars going this way in this slab, right? Which bars are these? Yes, temperature and shrinkage bars. Okay, so you have cover, the bar of the slab, and the shrinkage bars. And then you have to put your bars for the beams. So you're not going to put it right there, the same location, right? And so the 1.5 that we normally use will not be enough. So you have to think about placing those bars a little lower, right, from the top, so they can fit in the within the bars of the slab too. Okay. So that's why I assume now a value of 225. Okay. Right, so you will have more or less a value like that. So that's an approximation. Okay. I mean, we don't know. I mean, we haven't designed really the slab itself, so we don't know the bars, but you assume that. I mean, you got 3/4 of an inch is covered, right? So you got 3/4 of an inch plus the bar of the slab plus the shrinkage bar, right? And then this one has to clear those, right? And so that gives you, say you're using what? See, you're using number 8, for example, right? That would have been 3/4 plus 1 plus 1. That would be 275 minimum to cover that, right? If you are using number 6s, you would be okay, right? So you need a bit more distance here to put your tension bars on the beam because of the bars on the slab. Okay, okay. So you have those bars there. Okay, perfect. So with that, that clarifies the reason for the 225 here. And so that gives you reduced value for your D and D sub T. And with that, we find the A value. And then we find our F prime C. We know that. Beta 1 will be that. So we find our C. Do the ductility check. Plenty of ductility. Phi factor is 0.9. And A is maximum, right? A is maximum is satisfied. Okay, so now we check the capacity, and 150 versus 144, we're good. All right. Now the other thing is the distribution or reinforcement, right? We only have two number 10s here, so that will not be much of an issue, but there is a distribution or reinforcement that requires that if you have a B sub F that is less or equal than 110 L sub n, you need to spread your bars on the flange. Your B sub F is greater or equal than 1/10, and I think we corrected this, right? We changed it to greater. Yeah. Oh, wait a minute. Okay. Okay. Then you will use only 1/10 of L sub n. Okay? So really, if they are equal exactly 1/10, you get the same thing. All right. So for this case, 1/10 of L sub n will be 12 feet, 22 inches, divided by 10, 14.4. Okay. Our width is 14, so we're good. I mean, 14.4, 14, we're pretty good, right? So we're going to put our bars right in the middle, and then we're going to add some extra bars just for from the temperature shrinkage. Remember, you have bars coming from the slab on that direction. Those are your temperature and shrinkage. So you make sure that you have some of those bars covering some of this area on your flange. That's all. That will be more of a detailing rather than a design. Okay. And again, your spacing will be okay based on the 14 inches that you're using, right? And the C sub C again is with the 225. Don't forget that. So you have to put the stirrup, right? So you need all that in order to fit it in there. You don't calculate that. I mean, you're going to have your stirrups right in the middle of the bars, right? So those are things that you have to think when you're doing the detailing. Because that's going to happen. You're going to have bars in different directions. All the bars cannot be a 1.5 cover, right? So one's going to go below, the other one to go above, right? So you need to think about those. All right, so cracking control will be okay, so there it should be, right? And you can either do 2 number 8s plus 1 number 9. You can do 3 number 9s, 4 number 7s. You can do, so here I said, okay, 3 number 9s, we just work. Okay. Oh, we didn't match? Oh, because we got A75, right? Yeah, we only got 2 bars, right? We only got 2 bars within the 14 inches. And so that would have been 14 minus 5, 9. 9 divided by 1 is 9, and you're getting 8.4. So it doesn't satisfy. So you need 1 more bar to put in there. And so these are the options: 2 number 8s plus 1 number 9, or 3 number 9s, or 4 number 7s. And I just picked 3 number 9s. And so we're going to put 3 number 9s, right, in there. And this is what I was telling you about, right? So there is the cover for the bar from the slab, the temperature bars, that you have on the slab, then the stirrup, and then your bar, right? So definitely, I mean, that 1.5 is kind of tricky to put it there, right? And so you need a little bit more space. So these are simply extra 3 bars that you will bring from your temperature at shrinkage, right, to cover that 1/10 of your L sub n. For the exterior beam, we will do basically the same, okay? The tributary width is 3 feet, right, plus half of the beam width, so we know that, so that's 3.6 on the way there. So since the tributary width is about half the value for the interior beam, then the moments are approximately also in that ratio, right? And so I did a ratio simply here. So look at that. That's another way to simplify things. I did a ratio because the load is about that ratio. And then we get 145. And so using 3 bars to satisfy this cracking control, we use 3 number 7s. And 3 number 7s will give me 180. And that's greater than 145. And that fits, right? And so now that I got my bars, remember that I already got my dimensions because I already designed it here, right? So I'm not going to change my exterior beam dimensions. They're the same dimensions. So I already got my dimensions. I already guessed at my bars. So this problem now has become simply a problem of checking my capacity, right? I find my load, my live load, right? My load combination, my design load, my moment. Check my capacity with the bar that I'm using. I'm using the number 7s that I picked by doing the little ratio here, right? And again, we use the 225 just to have enough room to put our bars. Check for our flange, effective flange width, right? So the 3 equations, and 26 governs, so we use that. That one goes in the fact to use the minimum, so B sub F is 26, 2BW is 28, so now we use B sub F. So that will go here 26. Minimum is 129. We're putting 180, so we're good. Find our A value, check our ductility. Phi factor is good, right? And don't forget that. And AS maximum is satisfying, right? And I say that because some people like to have formulas for AS maximum, and you don't need those formulas unless you are specifically looking for that AS maximum number. Mm-hmm. All right, so then you check your capacity and it's pretty good. Mm-hmm. So that's it. So notice that I didn't do much work on this design of my exterior beam. I just went and used a ratio, right? Because that ratio will give me the ratio of the load pretty much, right? And then I pick a set of bars, and then I made the design more of a checking rather than a design, right? Because I already had everything. Okay. So look at it. If you have any questions, just let me know. Okay. But those are things that you can do to simplify certain calculations. Okay. Okay, the next thing is one-way joist system, so I'm going to stop here and we'll do joists in a different video.